Okay, thank you very much for this presentation, Rafael. And what corresponds now is that I'm going to tell you about this campaign, this measurement campaign about the number of particles that was performed in Santiago. It was a pioneering experience when it comes to the volume of vehicles that were measured. Also in the sense of using a team that has been recently certified in Switzerland for the control of emissions and the number of particles in the field. The purpose of this technology is actually to have applications for fiscalization. In what sense? In the sense that we can understand that these programs that have many benefits also must have a follow-up regarding on what are the conditions of their operation, and that would be the purpose of this presentation. So briefly, I want to mention the features of the diesel emissions so that we can understand why we are using this measurement system and why this would be the best system to do these controls. Here what we can see is the distribution of the particles according to their size, taken from a dilution tunnel, from a Euro 3 tunnel, which has a capacity of 350 particles per million. Now, what I want to highlight from this is that the size of these diesel particles, which are practically in a 100% under the other thing I would like to highlight from this sheet has to do with the behavior of a group of particles that we can observe as a second mode in this distribution, which corresponds to volatile particles, which means these are liquid particles that form part of these diesel emissions. But they have a different behavior, and they're generated or produced really in a very influential way due to characteristics of the environment, like humidity, like temperature, or other factors that make us think that these are products more than of the operations of the conditions of the engine, would be more of the conditions of the environment. So what can we say? These particles, the particles that come out of a diesel engine have a smaller size to 500 nanometers. Due to its smaller size, these particles can be really big in quantity but small in mass, which means that when we want to see the effect that a policy of mass reduction, we have to think that not necessarily we're going to reduce the smaller particles, but we could be reducing the bigger particles, which would make countersense because with the health, because size is a very important element. So we could say that this mass is the number of particles is the most important part of that. We've had examples of this in international legislation for emission controls, where we can see that technologies like Euro 4 or Euro 5 even do reduce the mass significantly without having an impact in the reduction of the number of particles. Now, the behavior of these particles in the organisms and their health are associated to the size of these particles. All of this concludes in that the incorporation of the measurement of the number of particles in the European regulation from Euro 5 to Euro 6, which means that we have to go to the number measurements. On the other hand, like we were saying, the diesel particles can be liquid, volatile, or solid, like black carbon that we've been talking about in previous presentations, and its effect on like a greenhouse gas, a pollutant, a greenhouse pollutant. The formation of volatiles depends, as we saw in the graph, more of conditions, of environment conditions and sample conditioning than the engine itself. Great part of these particles are emitted in a gas phase, and then they do condensation, which means that they're not particles when they come out of the engine, but they form due to the conditions of the environment. Now, the measurement of the number of particles, of volatile particles, these characteristics are not reproducible. So the conclusion is that the regulation for the measurement of MP means that we must eliminate the volatiles. So we have two components that are fundamental for these. It's to measure the number as a first element, and as a second element, to eliminate the volatiles as a part of what is being measured. For this campaign. Here we can see some of the conditions, like the range of the measurement when it comes to the concentration of the number of particles, that we can see in terms of our equipment, it exceeds this range that was established by the regulation, and it goes from the 1,000 particles to a million particles per cubic centimeter. Now, this is the regulation that I was mentioning regarding that the team has to accomplish. Now, the measurement method, basically, we were able to generate a cycle that contains 3 measurement points. In every cycle, we did a free acceleration that would allow us to get the highest value under the same conditions that we had before. Today, the opacity is being measured in free acceleration, and this is the same value in the same conditions, but measured as number of particles. Now, after the measurement in a stable condition represents the operation to most revolution, but in stable conditions, stable operating conditions, which was a second measurement point during the campaign. After that, we did an idling condition, which would be the third mode. Now, why do we choose these 3 modes? First, free acceleration as measurement of opacity. Like we said, we have a comparison parameter. Maximum RPM, as it is proposed today in Switzerland when it comes to this measurement for these equipment. Now, maybe this proposal, after this proposal, we could have other issues, but there's a procedure, there's a proposed procedure for these types of measurements. And the idling as the most simple measurement. Now, I have to tell you the story about this regulation of opacity regulation, and diesel emissions in Santiago began with idling opacity. Now, obviously, it came to a point where every bus was measuring 0, and then we went to free acceleration. Well, as of now, the fundamental difference is that there's a sensibility to it that allows us to measure in idling, where we can detect the emissions in that condition. Now, on the public measurements, I can tell you I want to say thanks also to the various departments that helped us with this procedure. Her director is right here, so Paula Flores. I want to say thank you as of now for your collaboration. Now, we joined the controls that the fiscalization department en route performs. Now, what they do a really professional type of control that allows to do all these types of testings in 3 minutes, which means that with 3 minutes of the bus being stopped, we are able to come up with these 3 figures. Now you can see as they are working with the measurements, you see that this is a random test in real operation conditions, and it is simple. It takes 3 minutes per test, and we get the values for number of particles and opacity. We also do these other type of backyard measurements, like we could call it, which our objective would be to calculate the efficiency with the measurements of before and after filtering. Here you can see the results. I have to say that these results are being debated on with the team, with the agency team, and also with the quality of air team from Switzerland, because we are with the challenge of being able to see how we can use this equipment to detect the filters, low efficiency filters with imperfections or malfunctions. Now, what's the logic of this analysis? First of all, it has their idling values, because from my perspective at least, the other values are there. They're not going to be presented here. We already know what idling is all about, because it presents facilities to when it comes ease of measurement in the public, and because today we have Euro 5 technologies that do not allow the control in free acceleration in an adequate way in the highway, because we have electronic systems that impede the maximum acceleration. So idling would be an alternative in this case. Now we can see that what we are aiming towards is the distribution of frequency with equitative logarithmic space. This has to do with the values that are the values that come from a dispersion from a range that is really big, that could go from the hundreds or thousands of particles to the millions of particles. So in order to be able to do a thorough analysis of these results, we we do a logarithmic scale so we can measure it. And effectively what we can see here and what we were expecting is these two distributions. As you see, a bimodal distribution where we can see the behavior of these filters, of high efficiency filters, and the behavior of another group of lower efficiency filters. So now what we're trying to establish is if there is or not a value, a reference value, where we could do the cut between the filters that are in good conditions and those that aren't. Now, why is this important? Because in the end, for the benefits that this program could bring, also for the measurements of the control and maintenance of the own companies, of the same companies, we need to be able to know with efficiency what is the value that can determine the selection or the determination of when a filter is in good or bad conditions. Now, if you see these backyard results, we saw that the group of filters that had low efficiency, and when we say low efficiency, we're talking about filters that were under an 80% of efficiency. We can see a distribution here of some of these filters that are near the 80% of efficiency, which means that probably they are repairable filters. Now, this is a small dent in the surface of the filter of a 1%, but that can generate a really abrupt fall in the filter's efficiency. So we are facing a group of filters that in this case could be repaired under these values. And to the value of 220 particles per cubic centimeter, which would be the point where we saw these two distributions separated themselves like a possible limit, we observed that effectively from the 22 filters that were measured with low efficiency, which means efficiencies under 80%, all of them practically had a value, presented a value by over this limit, which means that it's other than for one case where I think that to me it was an outlier point because this bus had really, really low emissions in a number of particles in both conditions, before and after the filter, which is very interesting. But we can see for all the other cases, this limit value could distinguish effectively these filters that were under the 90% of efficiency. So the results of this with the new filters, these would be the filters that are, it corresponds to all the other filters that were measured that were over 95% efficiency. Now, generally, more than 95, which was the initial criteria, we saw that they were even over 97% efficiency. And they would accomplish this reference value of 220,000 particles per cubic centimeter. Now, if we compare the results, what do we have? This would be one filter, a bus with a filter in good conditions. This is a bus without a filter. So now we see that buses with filters in good shape expel least particles than buses without DPFs or with malfunctioning DPFs. So the challenge is to be able to see how can we incorporate these control techniques so that we can improve the efficiency of the program, identifying which filters need maintenance or repair. Now, the number of particles, what can we see? Basically, the conclusion is that opacity is not a sensible enough tool to be able to detect the efficiency of a filter. As we can see here in this graphic where we use the opacity and the concentration of the number of particles, we can see that for opacity values closer to 0 in general, or for values to smaller than -2, we have variations in the number of particles between 4.5 or let's say 450 to 6 times 9, which would be, let's say, it would be like 660 million, 600 million of particles per cubic centimeter. So as you can see, the sensibility that we have when facing opacity is really a lot higher. Now, to clarify the range of the equipment, this value is higher than the range, because the value would only be to 5 million. But this equipment, what's the point of these measurements over the range? Effectively, it's a subestimation maybe of the value, because maybe the equipment has the capacity to be able to measure up to certain concentration, and above that there's interference between the particles, and maybe not all of them are counted as they should. I want to clarify also that in these values, these were the values reached by buses without filters. And in this, we should put our attention on that if somebody is going to put a value by over the exhaust pipe, we have to consider that the filter has an efficiency. So if we have these levels of number of particles in the engine, probably there is going to be also a high concentration for the output of this filter. Well, the conclusions. The international experience credits a percentage of failures, DPFs. Could be 2 to 3%. We'd have to see what values the program in Switzerland began with. Today I understand that they have rates of under 1%, maybe. But we have to be able to take charge of seeing this equipment that it does have a rate of failure. Now, if we think regarding to the efficiency results, many of these malfunctions could be repaired. Consider these values. Comes to the 80% that we can detect in many of those filters. And obviously the malfunction rates are not the same for all cases. And opacity is not a measurement system that's sufficiently sensible for all particles, and filters in good shape really reduce diesel emissions, which is the opportunity that we really want. That would be all. Thank you very much.